Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. And this is part 2 of a little mini series within that larger playlist of hypothesis testing. And here we're just doing some illustrations of two-sided uniformly most powerful tests. So in this video, in part 1 we looked at a shifted exponential distribution. In part 2 we're going to look at a uniform distribution from 0 to theta. We're going to have a sample size of n. Of course, xi has to be between 0 and theta, and this is for all I. Now, to find the uniformly most powerful test for this two-sided test, theta is equal to theta naught versus theta is not equal to theta naught, that's what we want to find. So here the density is 1 over theta. The joint density is, and this is restricted to, of course, this right here. And then the joint density is a product of these. But we set up a couple indicator functions that are going to help us in this test. And we set up 2 of them, which I'll show you in a second why. We could actually use 1 here, but then we have to use this trick next, so I'll just do it here. So if the minimum, it has to be greater than 0. And so if the minimum is less than 0, then it's really undefined, doesn't make sense. So the minimum has to be greater than 0, otherwise it's 0, and the maximum has to be less than theta. And so if that's the case, this is 1, otherwise it's 0. So they have to be between 0 and theta. Now we do that when we set up the likelihood function. So we take this joint density, put it here, but now we put theta 1 in the value, and then on the bottom we put theta 0. Right? Now look, this cancels and this cancels, and that's kind of why we broke it up. We're just left with this piece and this piece, which is over here. Now we're going to consider cases here. So let's let theta 1 not equal to theta, and let's do this simple versus simple hypothesis testing. And initially, let's assume theta 1 is greater than theta naught. And so by the Neyman-Pearson lemma, the most powerful test is this test function. So we reject the null when the likelihood is greater than some constant k, and we do not reject otherwise. Now, the value that we pick here is based upon this, what's called a side condition. So we set the expected value of our test function under the null hypothesis equal to alpha, which is this probability, and then we solve it for k. Now, let's look at this likelihood right here. And it's this. So this is the likelihood when we're less than theta 0, right? So this is a 1, and this is a 1, right? Because both conditions are met. Theta 1 is bigger than theta 0. So we just get whatever this value is, which is this. Now, when we're between theta naught and theta 1, then this is essentially undefined, or it goes to 0. So it blows up to infinity, or at least we define it as infinity, and then it's here. So this is an increasing function. Technically, it's a non-decreasing function, but my mind still thinks of it as increasing, which means that for this likelihood to be bigger than some k, that's equivalent to our maximum value being greater than some k. Now, so that means that our test function here is equivalent to this. So it's the maximum value is greater than some constant c. So the nth order, the density for the nth order statistic, or the maximum, is this, and unfortunately we're not going to derive that in this video to keep it at a good length. That's this, and the CDF for the largest order statistic is this. So now let's solve for alpha, which is expected value of the test function under the null hypothesis, which is this. Now notice here that the expected value is discrete. So it's this value times its probability, which is 0. This value times its probability, which is just a probability. That's why we have it right here. Now this is 1 minus the CDF, which is this, right? Plug in C. Now this is equal to alpha. We can back solve for C, and we get this quantity here. So that means the most powerful test for this simple versus simple hypothesis is this. So when our maximum value, our largest data point, the nth order statistic is greater than this cutoff, we reject, otherwise we don't. But notice there's no theta 1 value in this rejection region. So no matter what the theta 1 value is, this is most powerful. So that tells us it's uniformly most powerful for this one-sided hypothesis test. Now this part is, we're finished with it and we'll come back to it. So we've just proved, we've just have the uniformly most powerful test for this test. Now let's consider the other case where theta 1 is less than theta 0. And let's test this simple versus simple hypothesis test. Now when you look at the likelihood function, remember theta 1 is less than theta. And so when we're below it, then the likelihood is just whatever that value is. And then when we're in this region, the numerator is 0 and the bottom is a value, so we get 0. So this is a non-increasing function, and somehow my mind still likes to call it a decreasing function, which says to make it an increasing function in this statistic xn, we take its negative. And then so the negative of that, if we think of the likelihood as a function of this negative value, then it's actually increasing. And then we can say when this value is greater than some constant, we reject, otherwise we don't. Now, this is equivalent, so like if we multiply that -1 over, we get this, and then we have to switch signs. So xn is less than some constant, and this constant is technically not this constant, so I probably should have put a tick, but I didn't, and we'll just, this is the new C. So now we need to find C. So we set up this side condition of the expected value of our test function under the null hypothesis is alpha, which is this probability. And that's the CDF of the nth order statistic, which is this. Now we can back solve for C, and we get this. So that's the critical region. And so the most powerful test is when the nth order statistic is less than this value here. We reject, otherwise we do not reject. Now notice there's no theta 1 value anywhere. So that means it's the most powerful test no matter what the value of theta 1 is. That means it's a uniformly most powerful test for this hypothesis. You know, that theta is equal to that value versus that it's less than that value. Now, since both cases are independent of the arbitrarily chosen theta 1, this ends up being a uniformly most powerful test for this two-sided test. Right? So we just kind of combine them. So when xn is less than this value or xn is greater than this value, and we obtain these from the previous test. But one note is that in order for this to be a size alpha test, we have to divide the regions into alpha over 2. So like the left tail has alpha over 2 area and the right tail has alpha over 2 area. In order for this to be an alpha level test, it's the way that the power function limits as you're getting closer to theta naught. So we have to divide it by 2. Okay, well, this is all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.